Hello everyone. So today I will continue with the CTQ4. In the previous video of it, I explained about the concept of linearity. Little bit I go more in detail of the linearity, then we'll exactly come to the question. So yesterday what I was explaining about the linearity. Okay. So actually we have discussed whatever the system, whether it's a GM block or it is an amplifier block, we always look for the linear current or linear output voltage. It means the block should convert the particular input to the output with some linear relation. Okay. Yes. So what we have seen that any input to this particular block GM, it should convert this input quantity into the output that I call output current in a linear fashion. So also for this gain block, the same thing should be there, but is a linear relationship. So here what we see, this is my output, it is A times of V in. So I explained why linearity is important. Today I'll go and take the flashback. For the any MOSFET device, what we see in the characteristics for the MOS device, this is the characteristic. This is your ID or called the I out that the MOSFET converters. This is a VGS. I will also say it V in, and this I will call it I out. Okay. So what we exactly see, the complete relation for this is ID equal to, what is this relation? This is nothing but K by 2 WIL VGS minus VTH whole square. So what we can see there is I is proportional to V in square, or some additional terms will also be there, but it is a square relationship. So this is not going to fulfill my aim, that is nothing but I should be some constant K, which is a linear times of input voltage or input current, whatever, when we are looking for the output voltage. So yesterday I have taken the concept that usually what we do in amplifiers, we select a particular region, and in that particular region for the short span of time the characteristic is linear. Okay. So if we on the other hand, if we look for, so here I can say for this particular region, if I call about del ID, which is a very small current, you can say small region, is depending on some k times of del of V in. So it means, what this means, small incremental current is nothing but a linear dependent on the small incremental voltage. So a small incremental voltage. So this is a very understood thing, small incremental current, or it may some high values, but overall because of linear dependence for the very small part of the graph, we are seeing that particular output quantity depending on its input with some linear relationship. So for in general we can see this thing, if there is any particular block for which input output characteristic like that input output, any general block that can be, suppose this input relationship with the output is something like that, any random relationship, this is my input and this is my output. So if we write the complete equation, if we write the output in terms of input, it is a weird function which is not of any use. It is a totally means random function, any random function it can be. I am not taking particular function, it can be any random function. If I want to extract out this information, then I can see for any particular piece of part, I can say this is looking a linear. So if I am forcing my circuit or forcing my system such that it is operating in this region only, then I can say my output is dependent on the input with some linear relationship. In this region I can say my V out is k times of V in, because this relationship is linear. No matter what is the exact nature of my response or input to output curve, but for particular small region I can say it is linearly dependent on my input. Okay, so this is the motivation behind any amplifier scene. So when we look for a very large area, if I'm looking for this much region, then I cannot have the linear relationship. What we will have, I is nothing but quadratically depending on the input, some Vx, or can some constant times, that is Vth. Okay, so this relationship, so in this particular region if I am analyzing, then we can see that it is a non-linear dependence of the output current on the input. That's why we always analyze a small region and we amplify the signal. Now this things come to this problem. Actually the problem is what? If I talk about our actual problem, circuit 1 is what? I will not draw completely, but yes, the first particular block is my OTA block that everyone knows now. It has two inputs and it is generating a single-ended output. This is my input 1, this is my input 2. It is generating a single-ended output. And what is happening? This output is fed to PMOS. It is also operating from VDD to ground. Okay, so what is happening here? This is my VV naught that is coming to this transistor NMOS. Okay, so here we are driving a load, capacitive and resistive both type. So how we will look for this linearity and what is my motivation to take this circuit? So actually what is happening here, when we have designed the first circuit, what we have done, we have biased the input pair such that we biased the input pair with proper common mode, and an incremental differential. So what we can see, when we are designing the first stage for the first circuit, we have the input in our control, we have the input pair that are NMOS or PMOS type 5 transistor OTA. So this input has some common mode, and what signal we apply, actually we have the control. So what we will do, for the input pairs, we intentionally put some common mode there. I'm not drawing the complete structure, you can understand what I am saying here. You can see this is my 2I naught. Okay, so what is happening here, common mode is already applied, and what differential signal I have applied here is under my control, means a small signal we are intentionally applying. So what we will see at output, we have the current generated. This is nothing but an incremental current what is generating. It is nothing but GM of this transistor times this input voltage, which is an incremental small voltage. So I can say my output is nothing but this output current is the means depending on this incremental amount of the input. So I can say, suppose my these input pair are biased for the common mode, which is lying somewhere here. So suppose my transistor biased here, somewhere here, in this common mode, this I call VCM, and around it I am taking the advantage of amplification. So here I am applying this input. So this is in our control because we are setting the common mode and we are applying the differential input of the very low swing few millivolts or whatever the requirement. But so I can say the current which is generated by these device, or the small signal quantity that is generated by these devices, this current which is directly depending, linearly dependent on this differential input, which is like a gm vid by 2 and minus gm vid by 2. Okay, so this amount of current is in our control, so we can generate the linear current. So there is no problem of the non-linearity, we can control it because we have the input in our hand. But what will happen if I say on this point, what happen on this point, if I call this point x, what is happening here? Actually, here is some common mode that I will call bcm out stage 1 plus the signal. For a time being I will call it v in. This v in is not this v in, v in 1 v in 2, whatever the v in of the differential pair. Just for a time being I am just considering this node x has some common mode and some input. So is this input in our control? Because if we want a gain from the first stage, that we cannot say this is a small signal. This is now very large output, which is nothing but a gained output that I call the gain of first stage times the input differential that we have the first stage. This is the first stage input or differential pair input, first stage differential input. Okay, so this is a gain times of the input differential. So it is not in our control that this node will get only a common mode and a small perturbation around that. So what exactly happening on the second stage? What exactly happening on the second stage is that this is my PMOS. So here I have some common mode, I am not considering here, but okay, for time being I should write output common mode of the first stage plus this V in, which is coming out of the first stage. Or I should not write one, otherwise you will confuse with the inputs of differential pair. I will simply write a V in, but it is the output of first stage. You should keep in mind this thing. This is my current source, which is biased with the BV naught, as I call M5, M6. So this is my second stage. I have drawn only the second stage. Okay, so purpose of second stage is what? Because this input is swinging, the input that I call, I should mention here, otherwise some of you may confuse. So this is the output of first stage, which is amplified version of the differential input, output of first stage. Okay, this V in only, and of course this is a common mode output of first stage, output common mode of first stage. So this is happening now. This, so what we will see, this will be what we will see, the drain of transistor M6 is swinging a lot. Sorry, not drain, I missed it. Of course drain also, but the point is first here to tell you about the gate. Okay, so what you are seeing here, the gate of M6 is swinging a lot, okay. So it is not in our control that we have to apply some common mode. On top of that, we should apply a differential input signal of a small amount. Here already we are getting a large signal. So what on graphical level, what we can see, what is happening with the M6, if I draw the M6, of course it's a PMOS, but I am drawing the current like this. This is VGS of this M6. So what is happening here? Actually, if output common mode is somewhere here, that I will call what is a VCM out 1. So here we don't have the we don't have a small perturbation around this point. Actually, this signal swing is such that the first output stage signal swing is such that it is forcing my transistor on this large scale characteristics. So this point is directly saying that the ID has non-linearity with input. ID has non-linear relationship with input. Okay. So what should I do now? Actually you can do nothing, but now I will take this particular scenario is happening on the gate of the M6 or the of the uh, gate of the second stage transistor. So in any two-stage op-amp, when we will see in detail in the two-stage, first stage giving me some particular gain, and this particular signal is applied on the second stage. And second stage is getting what? Second stage is getting some common mode, that is fine for the biasing of my PMOS. If it is a if it is N type differential input first stage, then there is a PMOS for the second stage, who is taking the input. So what we are seeing that the input that is we are getting for the second stage is coming out of the first stage, which is already amplified input, because whatever the gain we get, the maximum gain we get from the first stage. So I'll just draw for a time being a stage. So if this is my first stage, let's say I'm just representing in my gain term. So if it is a first stage and this is my second stage, and what is happening, the signal that I am getting here X is already is, this is the main output. Okay, so this is V1, V2. So what signal we are getting is a large swing signal, because maximum gain what we get in two stage M is we get from the first stage. First stage is giving me the gain, almost all gain is provided by first stage. Usually in the design, if I'm designing cascode structure two stage op amp, for the first structure for the first stage, if I am using my telescopic structure with a wide swing current mirror, then I can see if total gain I am targeting that 60 dB, then more than or I can say more than 40 dB, more than 40 dB I get from the first stage, get from first stage, or more than that. Sometimes maybe this 60 dB completely is coming from the first stage. From the second stage we are getting a few dBs only, and depending on that we can say the major contributor of the gain is my first stage. So the signal which is coming at the X is not actually the small perturbation around the common mode, rather it is a large signal swinging around the common mode. So it is totally creating the disturbance for the second stage transistor, which is the M6 here. So what my M6 is taking here, it is a large swinging signal is coming at its inputs. So it is totally working in the non-linear relationship of its output current. So what we will see here, now we will exactly go to the first structure. Now my point is, I think you have clear idea about the point. So now I will see what these structures are used for. So this I am writing here V in just for the small signal. This is my ground. Then what you see, what we are seeing here, this particular node is swinging like if it is going down, what is happening, this is going up, because this is again a common source stage, M6 M5. This is my common source stage. I am calling it a small signal analysis, rather it is not actually a small signal, but for a time being I will say that it is something happening like this. So if this particular thing is going down, it is going up. So what is happening, this load cap which is available here, so it is charging through this. So the source current is, I am getting whatever amount we are getting, whatever required source current we are getting from M6. But what is the maximum sinking current? So if my Vin is going down, then output obviously will going up. So now if this my input is going up here, what is going here, this is going down. Okay, so now it has to sink the current, but what is the maximum amount that my M5 can sink? Maximum amount that M5 can sink depends on its own current. So I will not say here exactly the common mode, oh sorry, exactly the small signal, otherwise you will be confused, because here no small signal kind of phenomenon is happening. Okay, so I'll say here, wait for 1 minute. This is my VDD, this is my VV. No. So for the M5, its own current. What is its own current? It is nothing but decided by this VV naught. Because we are forcing the gate, VV naught means forcing the gate of M5. It means it is a voltage controlled current source. So my M5 is what? M5 is a voltage controlled current source. So it has its own limit. It cannot sink more than that. But due to the signal swing at the input, when my signal is going high, this is going low. It means this M5 should sink the current, but it cannot sink above its limit. So the limitation of the circuit is M5 cannot sink the current above its own limit. M5 cannot sink the current above its own limit. So what we will see here, now I will come at a current driving capability. From here we can see the second stage should have the large current driving capability. What is the motivation of second stage actually? So I will write here, motivation of second stage are two. Actually, it should be capable of driving. It should be capable of driving large capacitive load, cap load, and it should be capable of driving small resistive load. So this is the good second stage. So what you can see, its current driving capability should also be good. So other point is second stage current driving capability should be very good. Capability should be very good. So what limitation we are seeing in this circuit is that it cannot sink the amount which I require, because my signal at its input may swing depending on the first stage. But what we can see, it can drive or it can source the whatever the current amount of the current is required, because M6 has no other conflict of the current, because whatever the input going low at or high at the input of this M6, it is just generating the current depending on its VGS voltage, which is nothing but VDD minus Vin. So it is generating a current, and that current may be the sourcing current or sinking current. If it is sourcing a current, means Vin going low, so VGS is increasing, it is sourcing the current and capacitor is charging. And once the input is going high, so what amount of the current that VGS is reducing means current is reducing across the M6. So whatever current around across this M5 is increasing, or simply it mean this capacitor is discharging through the M5. So but M5 has the fixed current, so it is the I can say my sinking current is limited by this M5. So I can say that the current driving capability of this structure is not good, because it cannot sink whatever the amount of current is required. Rather, for the second circuit, whatever I have given in the question has a better current driving capability, because in the lower current means lower this what do you call means transistor like M5 has also the better current driving capability here, because there what we are seeing there for the input signal of the second stage means both the transistors are getting the same input. So we can see this thing. So what is happening in the second circuit, still the concept of linearity is not discussed here for these circuits. I am first going through the current driving capability. So for particular amount, this is I am only drawing the second stage for this second structure. So what is happening? There was a capacitor, and when this capacitor is shorted, both of my inputs are getting V in, which is nothing but output of first stage. This is the output of first stage. Other again no confusion, output of first stage. Okay. So I should write in better way. I will not write. So this is the output of first stage. So what is happening here? Yeah. So for the biasing purpose, it is getting biased from some other like this is a biasing source M5, this is M5, M6. So what is happening here? It has the common mode also, V out V C common mode of first stage plus V in, which is the output of first stage, the main output. Okay. So what we can see here, actually I want here I, and this is R and C. What I want, the target is that when the signal is coming, for the signal at input of second stage for the signal at input of second stage, it should be distributed to both the M6, and it should be distributed to both M6 and M5. So what ideally I should say, if I want my signal should be applied to both M5 and M6 at a time, so that I can have the better current driving capability, it is nothing but a work of inverter just. So let I'm seeing there is a high frequency, or the input which I getting from our output first stage, it is of high frequency. Whatever I apply, the differential input for the first stage has some sufficient frequency, so my output will have the same frequency. And for that particular frequency, if I'm considering my capacitor is shorted, and what we can see, the second stage is something like this. If I have enough frequency signal, then I can see this is my input. So this is nothing but overall a inverter structure which has same input applied at its both the inputs. So we can clearly see this thing. What is happening here? Whatever the requirement of current sinking and sourcing, it is capable of. Suppose this is going up, this node will go down, so it can sink whatever the amount it is required here. And when this is going down, it is going up, so it means whatever amount required can source. So sourcing and sinking for this structure is not restricted by any particular current source. So sourcing and sinking is not restricted by any particular transistor. So both transistors are adaptable to whatever the input changing at their gates. So whatever the inputs is changing at their gate, they can adapt according to whatever the requirement of current. So they can source or sink. So it has better current driving capability. So this structure has better current driving capability because it can source and sink any amount of current. It can source and sink any amount of current depending on its input. So this is the advantage. Current driving capability of this circuit is better than the first. Okay. So why there is a no conflict of sinking and sourcing? I should tell this concept. Okay. So if there is any particular transistor, I think some of you may have confused. That's why I am taking this thing. Is not required for this question, but I am taking. Suppose this drain node is fixed with some I naught. So what is happening here? So if my input is going low, what you can see here? So what is actually happening here? When the input is going low or going high, this actually gate is going low or high. So what is happening for this transistor? The BGS, this VGS is changing. Actually this VGS, just I am talking about the magnitude. Actually it is a negative, but BGS means magnitude. VGS is VGS changes. So what we can see, VGS is changing. It means there is always a problem. Okay, as VGS is changing, so what we are seeing, there is a current generation ID for this PMOS. Let I call as MP. There is a IDP which is generated due to this VGS voltage. It is generated due to this VDS voltage. Okay, due to the VGS voltage the current is generated. But what will happen here, actually this current is generated across this MP that I call IDP with some input voltage, and there is already a current source I naught. So here is my I, this is my CL. So there is always a conflict because in series two current sources are coming. So in series two current sources are coming. So what is the problem? Output voltage V out, that I will call more or like common mode, or whatever the amount of the output voltage will have conflict to set and means set a particular value on it. So this usually happens when two current sources are in series. So this is nothing but a voltage controlled current source which is due to the this PMOS, and this is general current source. So it can happen when there are two current sources in series, but actually it is the additional thing. It is not required for this question. For this purpose, what we are seeing, that just whatever amount it is sourcing, it can source any amount, but it can sync only required amount. That is the point. So current driving capability of second circuit is better. Okay, so conclusion is that current driving. So if you want to see why current driving capability and large capacitive load and small resistive load need to be supported by the secondary, you can read this thing in the Alan Holberg book that I already mentioned in the previous video, current driving capability for second circuit. So this is the takeaway from this, and for more knowledge of second stage you can follow Alan Holberg. Okay, so now I should go for the linearity concept of these two stages. Let I go faster. So what we can see here, there is an input, this node is swinging. So what amount of so this is my output. So what is the output actually? So what amount of current is generating here? This is my GM V in. So what should be the output? Output should be GM V in times whatever the R out at the output node. So usually we will see that output is coming at GM R out, that is GM of P, that I call GM of 6. Okay, this is my M5, this is my M6. Okay, so this is a GM of 6 R out. R out means complete R out. This is nothing but RDS 5 parallel RDS 6. So what we can see, if there is a non-linearity, the GM non-linearity, because this node is swinging a lot, so there is a non-linearity. So if there is GM non-linearity, what we will see, the output has a non-linearity. Suppose the GM6 that I will call GM6 V in, some higher non-linearity terms are there. GM6, let's suppose a dash V in square, GM6 double dash, that is a V and Q. It can have any non-linear terms, but for time being I am considering that there are two non-linearity terms are there, GM6 Vn square and GM6 dash Vn square. So Vn and Vn square. So second order non-linearity, if I am considering, just for an example, second order non-linearity in the output, second order non-linearity in the output is contributed by M6 only, because here is the only current which is generated by using this, it's a GM, the only current generated, the signal current generated by the M6 transistor here. But on the second structure you will see this current is generated by both the devices simultaneously. So we can see the non-linearity is more there in this second structure. Both have the input for some higher frequencies. What is the output? Actually the current that is generated here is GM6V in. What is current that is generating here? GM5V in. So it is looking like that I'm like writing only the linear terms, but actually there is a non-linear terms also that I am not writing here. Just I am showing that here this current is going down. This GM is non-linear function. This is a non-linear function M6 M5. So what exactly the output is we are getting here? GM5 plus GM6 V in R out. I am not writing R out again. Plus GM5 plus GM6 dash V in square, that R out. Okay, some higher condition. So for the for the second order non-linearity, we can see is more non-linearity in the second structure because both the devices are contributing to the non-linearity simultaneously. So more non-linearity can be observed here. A note or conclusion or takeaway: more non-linearity is contributed. More non-linearity is present in second circuit. Because of contribution of both M5 and M6 in the non-linearity. So this from we can see current driving capability wise means what I'll say, circuit 2 is preferred, and non-linearity, or I would say linearity wise, circuit 1 is preferred. Circuit 1, circuit 2. So what we can see, actually the important thing for ourselves. So conclusion is that current driving capability is important for us. Current driving capability is important. But what about the non-linearity that is coming due to this second circuit? Non-linearity can be suppressed. Non-linearity can be suppressed by negative feedback, because whatever circuit we are designing, second stage, two stage op amp, or whatever, we will use in the negative feedback. So negative feedback will take care of the linearity. Okay, so second circuit will be your preference. And now you can see extra things in the second circuit. Actually this the first circuit we call class A biasing of second stage, or this was my first circuit that I call the circuit 1. So you can read more about this class A and class AB. This is the class AB biasing, which is my circuit 2. So you can read more about this output stages of class A and class AB type, what is the advantage, and how you can understand more things about that. It is depending on you, whatever you want to study. You can see the Aaron Hallberg, Razavi, or whatever the online lectures. These are the important things. You can also follow the IEEE papers for this to class A, class AB, class B output stages. What are the advantages, what are the disadvantages of these? So the motive of this question was to tell you about what you can understand. So one thing that I missed here in the second structure, I didn't tell you about the RC concept that I mentioned in question. So actually there was one capacitor, and okay, this is my output, one biasing resistor that I call as RB, is called a cap. So why it is here? Because here what common mode we are getting is due to this output of the first stage, which is nothing but is adaptable for the PMOS. So here I want the common mode for 5 differently, that I call common mode of 6, better to say common mode of 6 instead of common mode 1, because it is coming from the first stage. So even I will call it a common mode of 6. This I call common mode of 6. So this common mode, yeah, I will say common mode 6 is coming out is good for PMOS, which is a M6, and it is not feasible for biasing of M6, sorry, biasing of M5. So what we will do, we will generate a different biasing for it, because what we are seeing in the first stage, whatever the common mode is coming out, that I will just go and flashback on it. This is my first stage. If first stage is of type n type inputs, if first stage of the n type input, then what common mode will it come at the output? What you will see, it will be of type VDD minus VDS of P. So this is a usual voltage that comes across this VDD minus VDS of this P. Or from the lower side, if you'll see, the minimum value of it is, you can see nothing but a overdrive of this VGS, or we can say whatever the common mode is here, plus 1 VT down of that. Okay, so this is the common mode range we know. Usually we have the common mode here such that VDD minus VDSP, or VDD minus some term, VDD minus some term, I can say it VDD minus some quantity. So this thing is good for the biasing of PMOS of next stage, not NMOS. If you want to bias the NMOS of second stage, just for the class AB structure, then what we will do, we will have this PMOS differential pair and NMOS as a current mirror. The structure will just flipped. Then what common mode we will get at the output, we can bias for NMOS of the second stage, not PMOS. But here what we are getting, input is the NMOS, but current mirror is of the P type. So what common mode we are getting is feasible to bias the PMOS of the next stage, not the NMOS. So for the NMOS of the second stage, we have to create the own biasing that I am generating here, called M5 or common mode of 5. Okay. So what you can see, ideally for the DC analysis, this cap is open, so it is getting its own biasing, that is a CM6, and M5 is getting its own biasing, which is a CM5. So for this particular, now if I want a signal, then what will have, what for the signal, for the signal I will say, if there is an input and here is capacitor and this resistor RB, what will happen, this node is ground, because for the signal purpose it is ground. This is also ground, this is also ground. For the signal purpose I am making it ground. So what we can see, ideally I want this input should completely appear here. So what we can see, what fraction of input is appearing at this gate of M5. We have to see what I will say, the input is appearing at this node X. What is the it is the input of M5. So Vx is what, from this you can see directly 1 upon, it is a high pass filter, 1 upon not 1 upon, I would like say, so what is this, this is RB divided by RB plus 1 upon CS. So what we will get from here, times this your input. So RBCS divided by RBCS plus 1 times my Vin. So if I want this Vx should nearly equal to Vin, and what is the chance we have, this RBCS should be much greater than 1. So that is Vx is equal to Vin. So from this we can conclude my RBC should be much greater than 1 upon omega of input. So whatever the input signal frequency we are using for the input of this circuit, the RBC should be much greater than this 1 upon omega n. So I think you can relate what was the point I was trying to mention here about this RC. So you can see from here. Or one more thing that we can say, suppose I have the RB and C already defined, then we can select the input frequency that we want to give to our circuit for this particular stage, so that this C is shorted at that frequency, and I can have this input of first stage to both the transistor of second stage, which are the M5 and M6. So this was this concept or this motivation behind this video. I think I have tell a lot of the things. I should recap from the starting what we have started. Okay, so from here I started the concept of linearity in the analog design. Is a very important concept. For more detail you can follow the books. It is already mentioned in Alan Holberg book that I already mentioned many times. I can also write here if you are interested, and you can follow. It is Alan Holberg. I think many of you have already studied it, Aaron Holberg. You can follow Razavi also. You can follow some video lectures as well that are available on the YouTube. Okay, so so this is the concept of linearity. In previous video I also explained. This video I also taken this into account. After that, the circuit one. So what we are getting from the first stage and what we are getting at the output of first stage, how it is causing the non-linearity for the second stage. You can see this thing. And so from here I entered into the current driving capability, which is our most important concept. Is also very important because the designing of second stage should be taken into the account when we are designing two-stage op-amp. The first stage is good for giving the gain, and second stage should take care of the how much swing you want at the output, how what particular load you want to drive. If it is a large capacitive load, if your second stage is good to drive the large capacitor at the output and a small resistor at the output, then your second stage is actually your design is good, and that particular your design of two-stage op-amp can be said good, because the second stage is capable of the responsibility of second stage is lot. It should take care of this swing. It should take care of the current driving capability. It should take care of what kind of load you want to drive. So these things I explained here. Now I've compared both the circuits, whatever I've given in the question. Apart from the questions, I've covered many things here. And okay, so what is the challenge when we have two current sources in series? You can see, and for more detail you can follow the books. Later I concluded here what are the constraints on this R, B and C, and for this particular design. So I think this is enough for this video. Thank you.